All right, this is section 7.1, sampling distributions. So we're trying to get to the point where we can take sample data and infer something about the population. So this chapter is going to kind of help us bridge that from what we've learned so far, and then getting us to the point where we can actually create confidence intervals and do a hypothesis test. So some things that we need to define here, and this should have been stuff that you read. So a parameter is just a number that describes some characteristic of a population. So mu is the population mean. Sigma is the population standard deviation. P is the population proportion. That's the symbol for population proportion. So then a statistic is just a number that describes some characteristic of a sample. So the sample mean is x bar. The sample standard deviation is s. A sample proportion is p hat. So the numbers themselves are the same. It's just where the things are coming from. So like I said, that's how they're related to each other. Like I could find the average height of all Fox Chapel area high school students, and that would be the mean. Or I could say I just want the average height of our class, and that would be a sample mean. The thing you just need to remember here, the P and the P. So a parameter comes from a population, a statistic comes from a sample. So if you look at this problem right here, you can identify the population, the parameter, the sample, and the statistic. Likewise, you can do the same thing here in this one. All right, sampling variability is just the fact that each time we take a sample, the value of the statistic is going to be different. So as I was talking about before, let's say I was trying to estimate the population average, the average height of all students at Fox Chapel area high school students. So if I was taking samples of size 30, there's multiple samples of size 30 I could take to find that x bar. So all those values would vary. That's just what we refer to as sampling variability. So there's an activity here, and some of your classmates got to do it yesterday. I had a bag of colored chips, and they were to take out 20 chips. In the bag, there was 100 blue, 100 red chips. They were to take out 20 chips, and they were to calculate the proportion of red chips. So if you look here, some of your classmates were able to do that. And what I just did is I put that all together. So as an example, Gabby got 12 chips. So 12 out of 20 gives you 0.6. Alex got 12. 12 out of 20 gives you 0.6. David got 12. 12 out of 20 gives you 0.6. So these were all different samples that people took of size 20, and they all had a different proportion. Now what we call this proportion is p hat, because it's a sample proportion. P is the symbol for the population proportion. So I'm going to switch this here. So then what I did with all those p hats that I had right here is I made a dot plot. But instead of using dots, I used p hats. Now I didn't get too many values here, so I'm putting some older ones in that I had before. But here's another one. And here's another one. And you can kind of see that these all, well, first of all, one thing you can see is that clearly there's sampling variability. So even when you looked at this chart, not every single sample gave us the same p hat. You can see the same thing when you look at this chart. You look at these charts from other years, likewise you can see the same thing. You can also see what values are likely to happen. So it's not really likely, if it's really 100 blue and 100 red in the bag, you're not likely to see values here at the extremes, which we didn't see across the board at all of them. We're more likely to see the values at around that 50% mark. So this sampling variability gives us an idea of what to expect from samples of certain sizes. So a sampling distribution is the distribution of values taken by the statistic in all possible samples of the same size from the same population. So here's sort of getting at what that sampling distribution is. So we took several samples of size 20 and I put them all together, and I'm trying to create a distribution of what all those sample values look like. The problem is I didn't create the true sampling distribution here because I didn't take all possible samples of size 20. So if I have 200 chips in a bag, there is lots and lots of samples of size 20. But again, like I was telling you before, this kind of tells us what to expect. So what do we expect if we take samples of size 20? What kind of p-hats do we expect? Like I said, it would be unusual to get things down here. So if we look at, let's look at your class. So if one of your fellow classmates took a sample of 20 chips and obtained 17 red chips, would you believe me that 50% of the bag has red chips? So if they got 17 red chips, we'd be way out here. If you look at any of these pseudo sampling distributions, do you see that value at all? No. So this kind of gets us to where we're headed. So when we see a value from a sample that isn't likely to occur, then that makes us suspicious about the original population. So if this happened, you would probably say, I don't really believe you that there's 100 red chips and 100 blue chips. All right, what's the difference between the population, the distribution of the sample, and the sampling distribution of the sample statistic? So the population was my bag, my big lunch bag. I had 100 blue chips, 100 red chips, and the proportion of reds was 0.5. Then I had each student. So Gabby took a sample of size 20. Allison took a sample of size 20. Alexa took a sample of size 20. So I had each student take a sample of size 20, and they found their own p-hats. And then what I did is I took all those p-hats and I put them all together. And again, I don't have every single possible sample of size 20. I only had about 13 or 14. But if I could put them all together, I could create that sampling distribution. So there's three different distributions here. There's population, there's each student's sample, and then there's one big sampling distribution. All right, a couple of things here. So there's a term here called unbiased estimator. An unbiased estimator means that the mean of the sampling distribution is equal to the true value of the parameter being estimated. So as an example, if I take a mean of all these p-hats, if it's equal to p, then it's an unbiased estimator. If I did something where I had a bunch of samples and I found the sample mean, so I found all the x bars, and I created a distribution of all the x bars. If the mean of all the x bars was equal to the population mean, so what I was trying to estimate, then it's considered an unbiased estimator. Likewise, if I found sample standard deviations, and I put all those sample standard deviations together, and the mean of all those was equal to the population standard deviation, then it would be an unbiased estimator. I could do the same thing for the median. Any statistic that I can take from the sample, I can create a sampling distribution for. And if the mean of that sampling distribution is equal to what I'm trying to estimate, it's an unbiased estimator. A biased estimator is one that's consistently higher or lower. How do you reduce the variability of a statistic? So if we wanted to reduce the spread here, what we need to do is take a larger sample. So if you look here below this example, so this is a sample of size 100. This is a sample of size 1,000. So this is just looking at, these values are going from 0.22 to 0.52. These ones are going from 0.30 to 0.43. So you can see that as you get that bigger sample size, the spread gets smaller. That's related to the sample size. So take a larger sample, you reduce the variability. As far as the population size has very little impact on the variability as long as that rule of thumb that we had last chapter is met. If this is not met, then we need to make an adjustment to the standard deviation. We are in AP statistics, we always assume, or we always try to fit this condition. We don't want to have to make that adjustment. So there's two key things here, this unbiased idea and reducing the variability. So that we have two things. So when we put those two things together, there could be 4 possible outcomes. You could have, when you're trying to estimate something, you could have something that has high bias, so it's completely off the target, what you're trying to estimate, but it has low variability. They're all very close together. All the estimates are close together. We could have something that has low bias, so they're surrounding my target, but it has high variability. They're way too spread out. This would be terrible because we'd have high bias and high variability. We're completely off and everything's spread out. This is the ideal. So we have no bias because everything that we're getting from the sample is like estimating what we want to estimate, and we have low variability, so they're all very close to each other. So that's the best case scenario. So another way to think about it is if you have no bias, you're accurate, so you're on your mark. If you have low variability, you're going to be more precise. And that is it. Tomorrow we'll do some activities with this stuff, and you need to do these problems. And you have lots to read and take notes on. So have a great time. See you later.